Hi everyone. In this video, I'm going to go over some questions from chapter 11 and 13 from your lecture course for general chemistry 2. And basically, these questions are designed to help you prepare for the test. But I should note, I didn't write your test or anything like that. So don't expect these to be the exact same questions that are on the test. Don't expect this to cover all the minutia that might be on the test, but it's a good broad overview of the concepts that you're going to encounter on your General Chemistry 2 exam. So use it in that way. Essentially, use this as practice. Don't memorize the answers to these questions. Make sure you understand how these questions are answered, and understanding those concepts will help you out a lot, hopefully, as you take the exam. So to be totally clear, I don't write your test. I haven't seen your test. I made up these problems or selected these problems based on my knowledge of what's in these chapters and the types of things that I would expect students to know after going through this material. Last thing I want to point out, especially for chapter 11, Lewis structures are super important. Now, I do not want to make this a 2-hour video, so I'm not going to go over all the details of how to write Lewis structures. If you are unfamiliar, have forgotten, or whatever, with how to write Lewis structures, I have pasted a link in the description below that goes over in detail. It's a whole playlist, it's about an hour long, in detail how to write Lewis structures. When I solve this problem set, I am going to focus 100% on the outcomes of the Lewis structures. Said another way, I'm just going to draw the Lewis structure there. So yeah, I'm not going to go over, put the least electronegative atom in the middle, distribute the electrons so that they have 8, the octet rule, stuff like that. So that's basically the purpose of this. Sorry, I'm rambling a little bit. Finally, and if you haven't used these videos before, you may not know this. If you look in the video description below, there is a list of questions and times. So if you just want to see specific questions, all you have to do is click on the time and it'll bring you directly to that question, so you don't have to watch questions you already know how to do. All right, so without further ado, let's get right into it. So this first question says, what is the strongest type of intermolecular force present in CH2O? This is formaldehyde. The Lewis structure of formaldehyde is this. And again, there's a link in the description below that goes over in detail how to get these Lewis structures. So in order of increasing order, the first type of intermolecular force is dispersion. All molecules have dispersion forces. This is induced dipoles caused by collisions and electrons getting knocked out of alignment, and then pluses and minuses, or partial pluses and minuses, attracting each other. The larger a molecule, usually we go by molar mass in general chemistry, but that's not always the case. It can also have to do with the shape and several other factors. But generally speaking, the larger the molecule, the stronger the dispersion forces. Dipole-dipole forces are present in molecules that are polar. So you have to draw the Lewis structure and decide if the molecule is polar. Hydrogen bonding forces are present if you have an O directly bonded to an H, and N directly bonded to an H, or HF, hydrofluoric acid. You have to have an H directly bonded to an F. The only common example is HF. So this is basically what you need to know. Ion dipole forces occur in mixtures. When you dissolve an ionic compound in water, for example, you would have an ion dipole attraction. These are even stronger, but they don't exist in pure substances. So this is not a mixture, so you're not going to have an ion dipole force. Generally speaking. So, and then of course none of the above. So now that you have a little bit of an idea of these intermolecular forces, let's go ahead and look at this one. So this molecule has dispersion forces because it is a molecule. All molecules have dispersion forces. Let's see if this molecule is polar. So in order to be polar, all domains must be the same. Well, here we have 2 hydrogen domains and 1 oxygen domain. They're not all the same. So this is polar. So if all domains are the same, it's non-polar. If the domains are not all the same, whether it's a lone pair or in this case an oxygen and 2 hydrogens, it's polar. So it has dipole-dipole forces. What about hydrogen bonding? Well, when it comes to hydrogen bonding, we need to have an O directly bonded to an H. And although this molecule contains an O and an H, they're not directly attached. So the strongest intermolecular force here is dipole dipole forces because it's polar and it doesn't have hydrogen bonding. So you notice we go through them one at a time. Nonpolar molecules would only have dispersion forces. Polar molecules would have dipole-dipole and dispersion forces, and molecules with an NH, an OH, or HF would also include hydrogen bonding. They would have dipole-dipole forces and dispersion forces as well. Question 2. We have the choose the molecular compound that exhibits dipole-dipole forces as its strongest intermolecular force. So I am going to directly draw the Lewis structures. Again, there's a link in the description below that goes over how to do this. So let's look at CO2. Carbon dioxide has 2 oxygen domains. Both domains are the same. It is nonpolar. So since it's nonpolar, the strongest intermolecular force is the dispersion force. H2. You don't really need to draw the Lewis structure of this because it's just a diatomic element. So the strongest intermolecular force is dispersion. If you only have 2 hydrogens bonded to each other, they have the same electronegativity, so it's nonpolar. You don't necessarily need to draw this. Ammonia. Ammonia looks like this. We have an N directly bonded to an H, so the strongest intermolecular force is hydrogen bonding, CF4. Notice that I'm drawing the Lewis structures of all of these before I decide what the strongest intermolecular force is. So for CF4, I have a nonpolar molecule because all domains are fluorine. So the strongest intermolecular force is, again, those dispersion forces. SO2. The best Lewis structure of SO2 looks like this. Again, you'd have to draw this out yourself. Okay, you're not going to be given the Lewis structures necessarily, so you do need to be able to draw them. And this molecule is polar. It does not have a hydrogen, so it can't have hydrogen bonding. So the strongest intermolecular force is those dipole-dipole forces. So that is our answer, choice letter E. Number 3 says, place the following compounds in order of increasing strength of intermolecular forces. Whenever you're asked to order things, which is several times on this problem set, when it says increasing, that means smallest first. I strongly recommend you take the 2 seconds to think about this in terms of smallest first or biggest first, so that you don't write it backwards, because I do see that happen sometimes, and I don't want that to happen to you. So think about, does it mean smallest first or biggest first? All right, let's draw out the Lewis structures. CO2, we already had in the previous question, so here it is again. F2, again, you don't really need to draw it because it's diatomic, so you know that it's nonpolar. And a very famous molecule, methylamine. This is from the show Breaking Bad. It's famous from the show Breaking Bad. And it looks like this. I don't know what that is. That's not meant to be electrons. So these are our molecules. Now, we want to look at the strongest intermolecular force in either of these, in all of these. So this carbon has 2 oxygen domains. All the domains are the same, so it's nonpolar. So the strongest intermolecular force is the dispersion force. F2, it's diatomic. Both F's have the same electronegativity. It's nonpolar, so the strongest intermolecular force is the dispersion force. If you're pressed for time, don't bother writing the Lewis structure of F2. You know it's dispersion. Methylamine. It is polar, but it also has an N directly bonded to an H. So this has hydrogen bonding. So we're looking at increasing strength of intermolecular forces with the smallest first. So we're going to label the one that's smallest as 1. Well, in this case, hydrogen bonding trumps dispersion forces. So hydrogen bonding is going to be the highest. So I'm going to write this as 3. Now, how do we deal with CO2 and F2, which both only have dispersion forces? Well, in order to deal with these, we have to look at the size. And in this class, size can be in terms of molar mass. That is not always the case, but here that's what we're going to go with. So I just find the molar mass of this, carbon and 2 oxygens. The molar mass is 44.01 grams per mole. The molar mass of this is 38, sorry, they're 19 each, 38.00 grams per mole. So since carbon dioxide is more massive, it's also physically bigger, than F2, it's going to have stronger dispersion forces because the electron clouds are more spread out, it's more polarizable, however you want to think about it. So that means that F2 is going to be the absolute lowest because we want smallest first, so it's 1. And the CO2 is going to be intermediate, so it is 2. And when we look at this, this answer, or this order, it ends up being choice letter E. So it says identify the compound that does not have hydrogen bonding. Now, in this case, we could go ahead and write out the Lewis structures. But what we're essentially looking for is NH, OH, or HF, which is the only example of a hydrogen bonded to a fluorine. So in order to have hydrogen bonding, you have to have an N directly bonded to an H, an O directly bonded to an H, or HF. If we look at NH3 ammonia, it clearly has an N bonded to an H. That has hydrogen bonding. This is methanol, found in windshield wiper fluid, among other things, and it has an OH. Water is probably the most famous compound with hydrogen bonding. It definitely has an O bonded to an H. HF is the example, so that has an H bonded to an F. And then we have CHF3. In this case, we have both F and H in the molecule, but you'll see here that they're not directly attached to each other. So since they're not directly attached to each other, this molecule does not exhibit hydrogen bonding, and choice letter E is our answer. Number 5 says, place the following substances in decreasing order of boiling point. So decreasing means biggest first. And as I mentioned in a previous question, whenever you're asked to order things in decreasing or increasing order, think about is it biggest first or smallest first. And it asks us about boiling point. But this is proportional to intermolecular forces. So it's essentially asking us which one has the largest intermolecular forces first, followed by the one that has the smallest intermolecular forces last. So if we look here, we have helium, argon, and bromine. These molecules are all elements, okay? So the strongest intermolecular force is dispersion forces. So since the strongest intermolecular force is dispersion forces, we care about molar mass or size. This is 4 grams per mole. This is 39.95 grams per mole. And this is 159.80 grams per mole. So if we look at the size here, we can see that helium is the smallest and bromine is the biggest. So we want decreasing order. So that means we want the biggest first. So bromine is the biggest, and it also therefore has the highest dispersion forces, followed by argon, followed by helium. And when we look here, this is choice letter C for number 5. Number 6 says, choose the substance with the lowest boiling point. So boiling point, as we mentioned in question 5, is proportional to intermolecular forces. So we want the one with the weakest intermolecular forces. So if we look at NBr3, NBr3 looks like this. And again, I'm just drawing the Lewis structures. So we can see this molecule is polar. It has 1 lone pair domain and 3 bromine domains. So this has dipole as its strongest intermolecular force. F2 is atomic, so it only has dispersion. So it can't be polar. H2O2. You don't really need to draw the Lewis structure here. This has an O bonded to an H. This is hydrogen peroxide, so it has hydrogen bonding. H2S. The same as H2O. This molecule is polar. It has 2 hydrogen domains and 2 lone pair domains. They're not all the same, so this has dipole-dipole. and CF2H2. So very similar to previous molecules we've seen. The molecule contains both fluorine and hydrogen, but they're not directly attached to each other. So this is polar because two domains are fluorine and two domains are hydrogen. So the strongest intermolecular force is dipole. So when we look at this, dispersion is the weakest intermolecular force, so therefore F2 has the lowest boiling point. Number 7 says, which of the following substances would you predict to have the highest enthalpy of vaporization? Enthalpy of vaporization is the amount of energy required to separate the molecules. So as we're going to see in a few questions later, enthalpy of vaporization is no temperature changes occurring, but we're adding heat energy to boil something, in the case of enthalpy of vaporization, because we have to separate the molecules. In a liquid, molecules are relatively close together. In a gas, they're far apart. The enthalpy of vaporization is the amount of energy it takes to physically separate them with no change in temperature. So this is proportional to intermolecular forces, because the stronger the molecules are held together, the more energy you're going to have to add to separate them. So let's take a look here. Cl2, this has dispersion. If we look at this, this is actually butane. Molecules that only contain carbon and hydrogen are thought to be nonpolar. So therefore, the strongest intermolecular force here is dispersion. Again, for propane, the stuff used in barbecue grills, this is dispersion forces because it only contains carbon and hydrogen. This is ethanol, the stuff that you find in beer and vodka. This, and in hand sanitizer, this has an OH, so this has hydrogen bonding, a stronger intermolecular force. And then CH3Cl has 3 hydrogen domains and a Cl domain, so it's polar, so this is dipole-dipole. So the one with the strongest intermolecular force is hydrogen bonding, because this has an OH on it, so it is choice letter D for number 7. Number 8 says, place the following substances in order of decreasing vapor pressure at a given temperature. So decreasing means biggest first, and we've talked about that several times. Now before I do this, I want to quickly go over what vapor pressure is. So if we think of a closed container, so there's some kind of stopper or something in here, all right, and my art skills are not the best, and we have some kind of liquid in here. Some of these molecules in the liquid phase are going to naturally go into the gas phase. If the molecule happens to have have enough energy and happens to be at the surface, it can evaporate into the gas phase. Now, pressure is essentially the number of molecules in the gas phase. So the higher the vapor pressure, the more molecules of gas, or more molecules of liquid that have become a gas in the gas phase. So when we look at this, if these molecules have a high intermolecular force, they're not very likely to go into the gas phase. If they have weak intermolecular forces, they are very likely to go into the gas phase. So vapor pressure is inversely proportional to intermolecular forces. Why? I'll explain in just one second. Or I'll re-say it in 1 second. If molecules have strong intermolecular forces, not very many go into the gas phase. So strong intermolecular forces means low vapor pressure. If molecules have weak intermolecular forces, they readily go into the gas phase, and therefore they have a higher vapor pressure. So it's inversely proportional to intermolecular forces. This is the only common property of molecules that's inversely proportional to intermolecular forces. We looked previously at enthalpy of vaporization or enthalpy of fusion, boiling point or melting point. Those are all directly proportional. But vapor pressure is inversely proportional. So I always put it on my tests. I'm not saying it's going to be on yours, but that's basically how it works. So now let's look at these molecules. The first one we have is PF5. And notice I'm drawing the Lewis structure of PF5. So I'm doing that here, so we have it. So if we look, once I finally get all these lone pairs in, there's a lot of them, okay, then basically you're going to see that all the domains of PF5 are fluorine. So this is nonpolar, so therefore the strongest intermolecular force is the dispersion force. The next one I want to look at is BRF3. So BR bonded to 3 Fs. In this case, the BR has 2 lone pairs. So now you have 2 lone pairs domains and 3 fluorine domains. So this is a total, they're not all the same. So basically 2 are lone pairs, 3 are fluorine. So this is polar, so this is dipole, dipole. Then finally, we have CF4, which I think we wrote before, but I'm not 100% sure. And CF4, all the domains are fluorines. So you get to draw lots of dots here because there's lots of lone pairs with all these fluorines on all these molecules. But all domains are the same. All domains are fluorine. So this is nonpolar, and the strongest intermolecular force is, again, the dispersion force. Now, we have 2 molecules with dispersion and 1 with dipole. So this is going to have the strongest intermolecular forces and therefore the lowest vapor pressure. So this is going to be number 3. This one's going to be last. Now let's look at these 2. We have to consider the size. Now, look, you don't actually need to find the molar mass to figure out that PF5 is bigger than CF4. Why? Because fluorines are the same size and phosphorus is bigger than carbon. So you have 5 fluorines instead of 4, and you have a bigger element in the middle. So this is definitely going to be bigger. But if you wanted to, you could calculate the molar mass, and it's 125.97 grams per mole. And here, it's 88.01 grams per mole. And I will tell you, this molar mass thing doesn't always work, okay? Sometimes you have to consider the shape of the molecule as well. We don't have an example of that here, but it does happen sometimes. So the dispersion forces in CF4 are going to be the lowest. That means CF4 is most easily going into the gas phase. So this is 1, and then PF5 is in between. So it's number 2, sorry. And that gives us letter B as the answer. 1, 2, 3, as shown in letter B. Number 9 says, how much energy is required to vaporize 48.7 grams of dichloromethane at its boiling point if its enthalpy of vaporization is 31.6 kilojoules per mole? So this is the amount of energy required to separate the dichloromethane molecules from one another at its boiling point, so without a change in temperature. So essentially to go from a liquid to a gas and with no change in temperature. So in order to do this, we're going to use dimensional analysis. And we're going to convert from grams of dichloromethane, CH2Cl2, to moles of dichloromethane, CH2Cl2, to kilojoules. And we know kilojoules per mole. So that's basically what we have to do. So starting with 48.7 grams of CH2Cl2 times, we're going to put 1 mole of CH2Cl2 on the top, and the molar mass, 84.93 grams of CH2Cl2 on the bottom, times, now we know the enthalpy of vaporization. It's 31.6 kilojoules per 1 mole of CH2Cl2. And when we do that math, multiply by the top, divide by the bottom, so on and so forth, we get 18.1 kilojoules, which is choice letter E. So basically, it's a stoichiometry problem / dimensional analysis problem. It's not really stoichiometry because we're not converting from grams of one thing to grams of another, but it is a dimensional analysis problem. Number 10 says, how much energy is required to heat 36 grams of H2O from a liquid at 65 degrees C to a gas at 115 degrees C? And then it gives us all the physical data that we need to solve this problem. The first thing I want to do is I want to convert this to moles. So 36.0 grams of H2O times 1 mole of H2O per 18.02 grams of H2O, and I find that there are 2.00 moles of H2O. So this is essentially going to be useful a little bit later on. So the next thing that I want to do is I want to write my phase change diagram. So in a minute, we're going to look at a phase diagram. Right now, we're going to look at a phase change diagram. And I want to put the milestones. So 65, in our case, is a milestone. So this is T in degrees C. 65 is a milestone. 100 is a milestone because it's the boiling point of water. And 115 is a milestone because it's given in the problem. So 65 and 115 are because they're in the problem. 100 is the boiling point, so we have to put that on there. And then over here on the x-axis, we just have heat going in that direction, heat being added. So what happens? Well, when we heat water at 65 degrees and it's still a liquid, it gets warmer. So as we add heat, the temperature increases. Then we get to 100 degrees and we add a bunch of heat and the water doesn't get any warmer because we're turning it from a liquid to a gas. So this is the phase change part. Then once it becomes a gas at 100 degrees, we heat it up. As we add heat, the steam increases in temperature to 115. And I'm going to break this into 3 segments. Segment 1, segment 2, and segment 3. So segment 1 is going to be from 65 degrees C liquid to 100 degrees C liquid. And the equation that governs what's going on here is Q equals mass times C sub S times delta T. The mass times the specific heat capacity times the change in temperature for segment 1. So this equals the mass of water, 36.0 grams, times the specific heat capacity of liquid water, 4.18 joules per gram degrees C, times the change in temperature. 65 to 100 is a 35 degree temperature change. So Q equals 5270 joules, or I'm going to convert it to kilojoules, divide by 1,000, 5.27 kilojoules. So this segment takes 5.27 kilojoules of energy to heat the water up. Segment 2, I'm going to move it over a little bit so I have a little bit more space. This is 100 degrees C liquid to 100 degrees C gas. So we're simply boiling the water. There is no temperature change, instead there's a phase change. This, Q equals N times the delta H of vaporization. N being moles. That's why I converted to moles a minute ago. So in this case, it's 2.00 moles times the enthalpy of vaporization for water, which is given on the table over here, 40.7 kilojoules per mole. When you do that math, you get 81.4 kilojoules. So it takes 81.4 kilojoules in order to convert the water from a liquid to a gas. Finally, 3. We're going from 100 degrees C gas to 115 degrees C gas. So we're again getting a temperature change. When we get a temperature change, Q equals MC sub S delta T. A big hint of that is the equation has delta T in it. In the case of segment 2, the temperature doesn't change, right? It's 100 liquid to 100 gas. So you're not going to get 0, right? You don't want to put 0 in here. Just a hint. All right, Q equals M C sub S delta T. The mass here is still 36 grams. Notice that the specific heat capacity of the gas is different. It's 2.01 joules per gram degrees C. It was 4.18 for the liquid. Times the change in temperature. In this case, it's 15 degrees. 100 to 115 is 15, so 15 degrees C. When you do that math, Q equals 1090 joules. I'm going to divide by 1,000, 1.09 kilojoules, like so. So I now have my three segments. What do I want to do to find the overall amount of energy added? Well, I want to add them all together. So I take 5.27 kilojoules, segment 1, plus 81.4 kilojoules, segment 2, plus 1.09 kilojoules, segment 3. And when I add those all together, I get 87.8 kilojoules. The answer here is 87.7, and the reason for the difference is a difference in rounding in one of these sections, but no other answer is really close to that. So this is how we can find the amount of energy for this phase change diagram. In question 11, we have a phase diagram, which is a little different than a phase change diagram in question 10. I know they sound similar, but they're not the same thing. So here we have pressure on the y-axis and temperature on the x-axis. So what we want to do is we want to label each of these sections, and then we can just pick the answer. So here, B, I don't know why I'm doing B first, but I'm going to do B first. We have low temperatures, right, because we're far to the left on the x-axis. So this is the temperature axis down here, and we're far to the left on the temperature axis. So low temperatures and everything but extremely low pressures. Well, at low temperatures, we know that things are solid. All right, and anything but extremely low pressures. Now let's look at A. For A, we have high temperatures, so far to the right on the x-axis, and extremely low pressures, so far to the bottom on the y-axis. At high temperatures and very, very low pressures, things favor the gas phase. The intermediate, C, is of course the liquid. D is referred to as the triple point. That one you just kind of have to memorize. And up here, it's not asked for, but this is called the critical point up here, above which you might have the supercritical fluid. You can have a supercritical fluid. So this is basically a phase diagram. There's questions you could be asked, such as, if you start here and you move this way, what phase change occurs? Okay, if you go from a solid to a gas, that's called sublimation. If we go from a solid to a liquid, that's called fusion in chemistry, so this is called the fusion curve. And if you go from a liquid to a gas, that's called vaporization in chemistry. So this is the vaporization curve. So basically you have the fusion curve, the sublimation curve, and the vaporization curve, in case you're asked about the curves. This is choice letter A. Question 12 says, which of the following statements is true? And the first answer is, in general, the solubility of gas in water decreases with increasing temperature. That is absolutely true. Warm soda goes flat faster than cold soda. That's just a way you can remember that. Gases tend to be more soluble at lower temperatures. Gases also tend to be more soluble at a higher pressure. That's why a can of soda is pressurized and the carbon dioxide doesn't come out. As soon as you open the can of soda, then the carbon dioxide starts to come out because the pressure has been decreased. The solubility of gas in water usually increases with decreasing pressure. That is not true. It's the opposite of that. The solubility of a gas increases with increasing pressure. That's why a can of soda is pressurized. In general, the solubility of a solid in water decreases with increasing temperature. There are a few cases where this is true, but for most things, the solubility increases with increasing temperature. That's why we sometimes heat things up to get the solute to dissolve. The solubility of an ionic solid in water decreases with increasing temperature. That's basically the same as the previous. And none of the above is not the right answer because A is the right answer. Dynamic equilibrium for a solution can be defined as, so essentially if we have a beaker containing some liquid and it has solute, in this case whatever the solute is dissolved in it, what's going on at equilibrium? Well, what's happening is some of this solute is dissolving while other solute is depositing. And at equilibrium, what's equal is the rate at which the dissolving, or the dissolution, and the deposition, or the reforming the solid, occurs. So this is a dynamic equilibrium because even though it just looks like there's some salt on the bottom, there's some of that salt is dissolving, and other of that salt is depositing. So what's equal in a dynamic equilibrium is the rate. the amount is not equal. You almost always have more solvent than you have solute, although it's theoretically possible that that's not the case. The amounts are not equal. The rate of bubbling is is greater than the rate of dissolving. I'm not even sure what that means about bubbling. Bubbling has nothing to do with this. And the amount of solvent is greater than the amount of solute. That's generally true, but that's not what dynamic equilibrium is. So that is, although true, not the right answer to this particular question. Question number 14 says, which of the following should have the largest Henry's law constant in water? So the formula is the solubility of a gas equals Kh times the pressure of the gas. So the solubility of the gas is directly proportional to the Henry's law constant. But we need to remember, like dissolves like. So the gas that is most like water is going to be the one with the largest Henry's law constant. So remember, when it comes to like dissolves like, that means polar solutes dissolve polar and ionic solutes, and nonpolar solvents dissolve nonpolar solutes. Well, water is probably the most famous polar solvent. So this is definitely polar. So we want something here that's polar. Well, Br2 is nonpolar. CO2, we've drawn it several times in previous questions, is nonpolar. CO, carbon bonded to oxygen, this is polar because one side's carbon and one side's oxygen. This molecule is ethane and it only contains carbon and hydrogen, so it's nonpolar. And neon is just an atom, so it's nonpolar, it's not bonded to anything. So the one that's polar, in this case carbon monoxide, is going to be most soluble in water and therefore have the largest Henry's law constant, Kh. Question number 15 asks us to calculate the molality of a solution formed by dissolving 34.8 grams of LiI in 500 grams of water. So in this case, molality, or in any case, molality equals moles of solute divided by kilograms of solvent. If you'll recall, in the past, you've learned molarity, which is moles of solute per liter of solution. Well, molarity changes as temperature changes because solutions expand when they get heated and they contract when they get cooled. So the concentration changes as the temperature changes. In a minute, we're going to look at some temperature-dependent properties, freezing point depression, for example, and boiling point elevation. So we want a unit of concentration that doesn't change as temperature changes. In order to find the molality here, we want to go from grams of LiI to moles of LiI, and then we want to divide those moles by kilograms of water. I'm going to do this like dimensional analysis. You could do it in 2 steps, find moles, find kilograms, and then divide. I'm going to do it in 1, but if you take the moles and divide by the kilograms, you get the molality, which is what we want. So if we start with 34.8 grams of LiI, we convert to moles using the molar mass, and it turns out that 1 mole of LiI is equal to 133.85 grams of LiI. Then we want to divide by the kilograms of water. Well, 500 grams divided by 1,000 is 0.5 kilograms. To divide in dimensional analysis, we put a unitless 1 on the top, and we put 0.5000 kilograms on the bottom. And when you do that math, you get 0.520 molal. Again, if you prefer, you can simply find the moles here, plug it in, find the kilograms here, plug it in. You'll get the exact same answer. Number 16 is another unit of concentration. What is the mass percent of vitamin C in a solution made by dissolving 6.5 grams of vitamin C in 55 grams of water? So mass percent, which is commonly used in, say, the healthcare industry, is the mass of the solute divided by the mass of the solution. And because it's a percentage, we multiply by 100. Now, percentages are the part divided by the whole. So remember that the mass of the solution is the mass of the solute plus the mass of the solvent. Now it's very important when you're doing these mass percent solutions that you read the question carefully, because sometimes they'll give you the mass of the solution and other times they'll give you the mass of the solvent. So in this case, it says, what is the mass percent of vitamin C in a solution made by dissolving 6.50 grams of vitamin C in 55 grams of water? Water is the solvent. So it is not the mass of the solution that you're given, it's the mass of the solvent. So in order to solve this, we need to take 6.50 grams divided by 6.50 grams, the mass of the solute, plus 55.0 grams, the mass of the solvent. You have to add them together because it gives you the mass of water. Unfortunately, I believe the answer is here if you leave this out. So you can actually think you got it right because one of the multiple choice answers is here. But you want to just go ahead and make sure you add them together if you need to. We multiply that by 100 and we find that the mass percent is 10.6%, which is choice letter B. Another unit of concentration is mole fraction. And it says, what is the mole fraction of I2 in a solution made by dissolving 55.6 grams of I2 in 245 grams of hexane? So the mole fraction is equal to the moles of solute, in this case I2, divided by the total mole. The only difference between a fraction and in this question and a percentage in the previous question is the you don't multiply by 100. Now it's different because the units are different. In the other case it was grams, in this case it's moles, but we don't multiply by 100 here. So we need to find the total number of moles, and we also need to find the moles of I2. So we need to convert both of these grams to moles using molar masses. So starting with 55.6 grams of I2 times 1 mole of I2 per, the molar mass of I2 is 253.8 grams of I2. And when you do that math, you get 0.219 moles of I2. Now we want to repeat that math for the hexane, and that is 245 grams of C6H14 times 1 mole of C6H14 per the molar mass of C6H14, which is 86.18 grams of C6H14. And when you do that, you get 2.84 moles of C6H14. Now, when you're doing this, now that you have the moles, you simply plug into this equation. So the moles of I2 is 0.219. And the total number of moles is the moles of I2, 0.219, plus the moles of hexane, which is 2.84. And when you do that math, you get 0.0716. And you'll notice that that's slightly different than the answer that they got, 0.0715. That's because of a rounding difference, but that's what I got on my calculator. I'm going to go ahead and select choice letter B. Question 18 is just a definition. It says, what is a colligative property? You just have to know this. A property that depends on the number of particles in solution, but not the nature of the particles. So freezing point depression, osmotic pressure, boiling point elevation, these are all colligative properties. So it depends on how much stuff is dissolved in solution, but it doesn't depend on what is actually dissolved. So this is important because this is, in the lab we talk about this as well. So it's just something you have to, unfortunately, memorize. Question 19 says, determine the freezing point depression of a solution that contains 30.7 grams of glycerin in 376 grams of water. And then it gives you the Kf of water, which is 1.86 degrees C per molal. So the equation that we want to use is delta Tf equals I, the Van Hoff factor, times Kf times m, the molality. Now the Van Hoff factor is the number of ions that the solute breaks up into its solution. Well, this is a covalent compound. It only contains carbon, hydrogen, and oxygen. Said another way, it doesn't contain a metal. So this I equals 1. In question number 21, we'll talk a little bit more about the Van Hoff factor if you're not sure about that. So you might want to watch that one as well. I haven't gotten to it yet, but by the time you see this video, I will have. Kf is the constant given here, and M is the molality. In a few questions back, specifically question 15, I calculated the molality. Sorry, I moved the paper there. All right, so let's go ahead and do this. So the first thing I want to do is calculate the molality of the glycerin. So I want to go from grams of glycerin, I'm just going to abbreviate it gly, to moles of glycerin. And then I want to divide those moles by the kilograms of water. And moles divided by kilograms will give me the molality. You can do it in 2 steps or 1. I'm going to do it in one-dimensional analysis, but it doesn't matter. So I'm going to start with the 30.7 grams of glycerin times 1 mole of glycerin per 92.09 grams of glycerin. And then I want to take that and I want to divide it by the kilograms of water. So I want to take 1 over the mass of water in kilograms, so not 376, but I got to divide that by 1,000, which is 0.376 kilograms. And when I do all that math, I find that it's 0.887 molal. Now I can plug into this equation. I is 1. Kf is 1.86 degrees C per molal. And the molality is 0.887 molal. When I do that, I get 1.65 degrees Celsius. So the freezing point depression here is 1.65 degrees Celsius. Question 20 says, choose the solvent below that would show the greatest boiling point elevation when used to make 0.1 molar non-electrolyte solution. So delta TB equals I KB M. In this case, I and M are constants. They're not always constant, all right, but they're constant here. Why? Because all the solutions are 0.1 molal. That makes M a constant. And it's a non-electrolyte solution. That makes I a constant. So, to be clear, I and M are not always constants. In the previous question, we had a value for molality, okay? But in this particular question, I and M are constants because of the way the question is worded. It's a non-electrolyte solution, I is 1, and it's 0.1 molal in all cases. So in this case, the only thing that matters is KB. Well, the one with the highest KB is going to have the highest boiling point elevation. So if we look through here, we find that carbon tetrachloride has a KB of 5.03. That is the highest KB, and therefore the highest boiling point elevation. Question 21 says, identify the solute with the highest Van Hoff factor. So the Van Hoff factor plays a role because in colligative properties, it's dependent on the number of particles in solution, but not on the nature of those particles. So we need to see what happens to these different compounds in solution. So the first thing we need to notice is that Ki is ionic. So when Ki dissolves in water, we get K plus, it's a 1A metal, aqueous, and I minus, a 7A nonmetal, a halogen, like this. So I equals 2, because Ki breaks up into 2 things. Now you have 2 particles in solution, you'll have double the effect of the freezing point depression. C6H12O6. This is a non-electrolyte. How do I know? No metal. It's a covalent compound. It does not break up into ions in solution. It will dissolve, but it will not break up into ions. So I equals 1. AlCl3. We get AlCl3 as a solid, which breaks up into Al3 plus aqueous plus 3 Cl minus aqueous. So in this case, we get 1, 2, 3, 4 ions in solution, I equals 4. Magnesium sulfate. This one's tricky because it has the polyatomic ion sulfate. It's important to solve these problems that you recognize your polyatomic ions. So magnesium sulfate, solid, breaks up into magnesium, 2 plus, a 2A metal, aqueous, plus SO4 2 minus sulfate, a polyatomic ion, aqueous. breaks up into two things, I equals 2. Calcium chloride, CaCl2, solid, breaks it up into Ca2 plus, aqueous, plus 2Cl minus, aqueous, running out of space here, but it breaks up into 1 calcium and 2 chlorides, or a total of 3 things, so I equals 3. In this case, the highest Van Hoff factor is AlCl3 because it breaks up into 4 things in solution. Question 22 says, choose the aqueous solution below that has the highest boiling point. These are all solutions of non-volatile solvents, and you should assume the ideal Van Hoff factors were applicable. So delta TB equals I KB M. In this case, since it's all water, KB is a constant. And also, they're all 0.1 molal. They're all 0.1 molal. So these two variables are constant. In question 20, different variables were constant, and the KB influenced what was going to happen. I and M were constant. In this question, KB and M are constant because it's the same solvent and the molalities are all the same. So what matters is I. Well, what happens when we dissolve BaCl2 in solution? So if this is a solid, we get Ba2 plus aqueous plus 2Cl minus aqueous. I equals 3. This is covalent, and it was in the previous question, so I equals 1, number 21. AlCl3 was also in the previous question, and it breaks up into Al3 plus aqueous plus 3Cl minus aqueous, so I equals 4, because we have 1 aluminum and 3 chlorides as discussed in the previous question. LiBr breaks up into Li plus aqueous, 1A metal, and Br minus aqueous, it's a halogen, I equals 2. So the one with the highest Van Hoff factor, aluminum chloride, is going to have the highest boiling point elevation because Kb and M are constant. Last question, it says, when 0.150 grams of an unknown non-electrolyte compound are dissolved to make 1.05 liters of solution, the osmotic pressure of the solution is measured to be 0.0288 atmospheres at 25 degrees C. What is the molar mass of the compound? Well, the osmotic pressure equation is just a rearrangement of the ideal gas law. And it's C, in this case when we're solving for concentration, equals pi, which is the osmotic pressure, over R, 0.08206 liter atmospheres per mole K, T, which is the temperature in Kelvin. C is the molarity, moles per liter, or said another way, it's N over V. So it's just a rearrangement of the ideal gas law, PV equals nRT. Now, this is the equation we need to solve this. So the first thing we want to do is we want to find the concentration. From the concentration, we can find the moles, because we know the volume. And then from the moles, we can find the molar mass. Normally, if you want a molar mass, you just look it up on a periodic table. But here we want an experimental, if you will, molar mass, which is grams per mole. Well, grams is easy. It says 0.150 grams of an unknown non-electrolyte compound. So therefore, we know grams. Moles, not so easy. We got to figure that out. So concentration equals pi, the osmotic pressure, 0.20288 atmospheres, divided by the R, 0.08206. I'm not going to write all the units out every time, times the temperature in Kelvin, which is 298 K. If you want 298.2 K, it's 298.15. Whatever you want to put, it's not going to make that big of a difference. I'm just going to put in 298 K. When you do that math, you get 1.18 times 10 to the minus 3 molar. And molar is moles per liter. So we have a 1.18 mole, times 10 to the minus 3 mole per liter solution. But we have 1.05 liters of it, so we can figure out how many moles are in that solution. So if we take that and we multiply by 1.05 liters, liters cancel out, and we know that there's 1.24 times 10 to the minus 3 moles of solute in this solution. Now, I guess I wrote it a little low, we can find the molar mass, grams per mole. We know the grams, it's given in the problem, 0.150 grams. We know the moles because we just found it, 1.24 times 10 to the minus 3 moles. And when we do that math, we find that it's 121 grams per mole, which is choice letter A. So that is it for the problem set. I would just want to remind you again that you can download a copy of this problem set as well as the answers in the description below. You can also find the times down there, so you can click on the individual time. And then for the beginning part of the problem set, we do a lot of Lewis structures. If you would like to review how to do Lewis structures, I have pasted a link to a playlist from earlier videos that you may have seen before, just to give you a reminder of how to write Lewis structures. Thanks for watching.